Welcome back. I hope you've made some decisions about the hypothesis. Remember, we're going to be investigating the period of a pendulum and what factors affect the time it takes for that pendulum bob to swing backwards and forwards. So let's get straight into it. Here's our pendulum that's set up, but I'm going to go to the simulation, and the first thing I'm going to do is I'm going to say, here's the bob, and let's just do a little bit of playing to start and show you that it can swing backwards and forwards. This simulation is quite nice because it marks the angle at which it swings. So I can stop it over there, and you can see that it's stopping quite close to the point of no return. The second thing I want to just do carefully is to show you how we can move it through a cycle. I'm slowing it down. So starting there, the pendulum would go all the way through until it's reached the maximum at the other side, and it comes back to the equilibrium position and back to that point. That process of swinging backwards and forwards is one cycle. And that is the time taken for one cycle is the period. Now, to measure this accurately, we're not going to measure from the point, if you're doing it with a real pendulum, this pendulum is a non-frictional pendulum because it's a program. But if we were doing it with a real pendulum, we'd always measure from the middle point. And even here, I've got a little device that shows me the period timer. So I'm going to make it a normal speed now, and I'm going to show you how it will measure the period, and it will trace the period for you. And you'll see it's the same thing. So starting from the middle, it measures that time. And you can see it's measured from the middle to the maximum position, then back to the middle, back to the maximum, and back to the middle again. So the period you'll see there is able to be measured, and we're getting the same sort of time for two tests periods. So you'll see what 1,72 was the data that we got there, and if I did it again, we would find that it's consistent. It's not going to change much. Let's just do one more so we can see. And there you go, 1,7283. And so this process is going to be dependable. It doesn't change just for nothing, but it changes when we affect a change. So the first variable that I'm going to do, and I'm going to just stop this, I'm going to keep the length of the string at a set amount, 0.7. I'm going to change the value of the mass piece. And over here, I'm going to change the value of the mass piece. Let me just make sure that I've got the right values. I can change the values here. I'm going to make that one 0.2 kilograms. I'm going to try and keep the angle of release at 40 degrees, and let's let it go, and let's collect that data. So the length we're going to keep the same. The mass is 0.2 kilograms. Gravity and friction we're not going to interfere with, but let's let it swing, and let's measure the period. And this time, the period is 1.73. I'm just going to pause it, 1.73, because I want to record this data. And I've drawn up a table already where I've got the mass in at 0.2, and if I remember correctly, the period we've measured here is 1,73. Now, let's have another look, and let's change the mass to 0.4. So instead of the mass being, let's change it, make it 0.4. We're almost there. And let's make sure that we release it at 40 degrees, and there we're going to let it go, and I'm going to measure the period. And what do you notice? The period is still 1.73. That's quite amazing. You might have not selected that as part of your hypothesis, but whatever it is, we're able to compare our results now. But maybe it was a fluke. Maybe it wasn't just, it was, so let's try it again. Let's try it again and do one more swing of this mass. We recognize we're keeping everything the same, and let it go from that position, and we'll measure it one more time. 1.73. It looks like it's consistent. And you see, if we were doing this in real life, we would take lots and lots of readings. And in fact, what I can do now is say, well, maybe let's just increase the mass again to 0.6. And let's try it again there. Check that point. Check the period. 1.73. It's done it again. It doesn't look like mass has an effect on the period. But just to be very clear and very safe, let's increase the mass again to 0.8. And if we do that, keep the angle the same, and we're going to keep the angle the same, and then measure the period. And what have we got? We've got 1.73 again. So it doesn't look like mass has an effect on the period. Let's go and write down our results, and we can see that it looks like that in every case we got 1.73. And I would predict that if we had 1.2, it would also be 1.73. Let's just go and confirm that that is the case. See, I didn't put 1.2 in, so let's put the 1.2 in, do one last swing, stopping at this position, starting there, let it swing, measure the period, 1.73. So we're absolutely correct in terms of what we've done. Now, notice that I'm not changing anything else. I kept the length the same, I kept the angle the same, and I only changed the mass. So in this next experiment, or this next trial that I'm doing as part of this investigation, what I'm going to do is I'm going to change the length, but I'm going to keep the mass the same, and I'm going to keep the angle the same. So let me just check with you so that you can see. On my data that I've collected over here, I'm going to start with a long mass, a long length at least. The mass doesn't matter, keeping the mass the same, the length of 1 meter. And I'm going to let the length decrease. And I'm going to measure the period and see what happens. So let's go to the board. Let's keep the mass at 1 kilogram, just to make it nice and round. And let's take that to 1 meter. We'll keep the angle that we've released it from as 40 degrees. It could be 40 degrees on the other side, doesn't matter. And let it go. And as you can see, the period has increased. The longer string, the longer the mass, it looks like we've got a longer period. But let's write that data down. It was 2,068. I'm going to round that off to 2,07. 2,07 for 1 meter. 2,07. Now we're going to go and look at 0.8. So over here, we're going to change the mass, the length of the string to 0.8, and let's get going. Collect the data, start, measure the period. Okay, 1.85. 1.85, record my data, 1.85, and we're doing well. So let's go to the next one. We're going to go to 0.6, I think. We said 0.6, and we're on that position, and we're all good to go. $1.60. Write it down. Oh, that was, I didn't put 0.6. Let's go to 0.4. I know why I did that now, remember, but you can see that the trend is that it's getting smaller. 0.4, let's swing it, start it, and there we go, 1.031. 1.31, I think. Let me just double check. 1.31, we rounded off to 2 decimal places. And then if you look back over here, 0.2 is what we want to be on. So this was 0.4, we want to halve it, 0.2, and let's just stop it, and let's make sure that we start it in the right position. 40 degrees. There we go, starting there. And you can see as you're looking at it, it looks like it's swinging faster. And exactly, 0.93 is the period there, 0.93. So have a look at our data that we've collected, and what's the trend that you can see? Certainly, it looks like length has an effect. As we decreased the length of the string, we found that the period decreased as well. If you read the data from the bottom up, as the length increased, the time that it took increased. So it doesn't matter whether we look at it from the top down, a decrease in the length, or an increase in the length, the trend is the same. As the one increased, the other one increased. As the one decreased, the other one decreased. But did they do it in the same sort of relationship? Well, that we're going to have to spend a little bit of time on and have a look at in a second. The next idea that we want to do is just check the angle very quickly. So if we check the angle and say, does the angle make a difference? Now I want to make this a bit longer, make it 1, and let's have a look at changing the angle. So I'm going to stop it for a minute, and I'm going to say, let's start at 10 degrees, which isn't very far off the middle, and let it go, and we're going to measure the period. And that gives us roughly 2,01. Let's increase the angle a little bit, and we're going to make it 20 degrees. And that goes up to 2,02. So it looks like it's changing a little bit, but not by very much. And so this was 2,01. This is 2,02. So there's a small change, but it isn't a very significant change. If we go to 40 degrees, we've doubled that. We recognize we swing this one now, measure the period. It's also in the region of 2,06, almost exactly the same as before. Small difference, 2,06. There is a change, but not by very much. And we're not if we go all the way to 80 degrees over here, let this swing, measure the period, and you can see over here now, there is a fairly significant change, but it doesn't seem to be very consistent. 2,2 is the answer that we're looking for there, and 2,2. So as the angle increases, it does have some effect, but not a huge effect. We're going to need to analyze this data and compare it to what we originally thought by looking at our hypothesis and seeing if we can work out exactly what's happening. But you know what? I think it's time for you just to look at the data, and let's take a short break.